Yes, where are we in physics? Up until now, we've studied the most basic form of motion, okay? Um, and this lays the foundation for everything that happens in physics because most of the things that happen in the physical world involve some kind of motion, right? But it begs the question, how did motion start, right? And what is responsible for changing motion? Okay, and that is where we're heading into now because there's only one thing in the entire world that has the power to either start motion or change motion, and that is a force. Okay, forces cause accelerations, and accelerations result in the change of motion of objects. And this entire chapter is dedicated to exactly that, right? Studying the forces that actually have an effect on the motion of various objects in the universe. Okay. I'm going to warn you ahead of time. This is a dense chapter. This is, you probably have realized that chapters get a little bit tougher every week, and this chapter is probably the peak so far. Okay, and I would say it doesn't get a heck of a lot harder than this, but this is going to be the most challenging thing you guys have come across so far. Because in many ways we're tying together everything we've learned and we're learning another way of looking at the world, and it's through this lens of forces. Okay, so this week I want to start out by doing a little bit of review, and that review is hopefully something that you guys have heard about before, which are Newton's 3 laws of motion. Okay, before we get there, I want you guys to advance to the quote of the week. It's from somebody who maybe is very famous to some of you, named Tony Robbins. He is considered the first, real motivational speaker, and he says the only things that are keeping you from getting what you want are the stories you tell yourself. And so I think this is a very nice reminder that a lot of the times, if we're not content, the real reason is because we're tripping over our stories. Okay, we're tripping over the stories we tell about ourselves, about what we're actually capable of, what we deserve, and whether or not we belong in a certain field, like let's say science, or it could be any story that keeps you from getting what you want out of this one chance at life that we get. So this is just kind of like a reminder to be aware of those. Be aware of those stories that come up that you can kind of trip over on your way to living the most fulfilling life, living your best life. Okay, advance to why do we care? I think this is a very interesting question. Does anyone know how fast a raindrop actually moves? Okay, how fast would that raindrop plops on your head? What speed is it actually going at? In this chapter, we will be able to determine that from nothing else. Just knowing gravity, we can determine what the speed will be of a raindrop falling on your head. Okay, and I'll see you there on the last slide when we go over that. Okay, so if you can go to the next slide that says Newton's first law. There's certain things in physics, like E equals mc squared, that are major parts of popular culture. In other words, they're things that everyone has heard of at some point, okay? One of those things, I think, is Newton's first law. Almost everybody's heard the phrase, an object in motion will stay in motion, an object at rest will stay in rest, unless acted on by an outside force, okay? So I want to talk a little bit about what that means. It's something you've heard a million times in pop culture, so what does it actually mean, okay? Well, I'm going to start by saying a few other ways of saying the same thing, okay? I think sometimes when you hear the same sentence for years and years and years, it gets a little bit stale, right? And you forget what the actual meaning is. So another way of saying it is that an object's motion cannot change unless an unbalanced force is acting on it. And the next slide, I'm going to show you guys what an unbalanced force is, right? Another way of saying the same thing is an object will only accelerate if a force acts on it, okay? And a third way of saying it is that an object's motion or lack of motion will continue for eternity unless it's acted on by an outside force. You wouldn't think that this was so groundbreaking, but this was huge. Everything you get to enjoy in your lives right now, right? Everything from automobiles and transportation to even simple things like electronics comes from the fact that we were able to determine this first law and then the two other laws that kind of spring forth from it. right? That Newton came up with. Interesting enough, in his own time of quarantine, in the 1600s in England. So quarantine is a great time to be creative. So what this is essentially saying is simply that you cannot get motion to change or to start unless a force acts on an object, right? And this was so groundbreaking because for years and years and years, the Greeks, especially Aristotle, said that the natural state of any object is rest. Objects always want to be at rest, and that whatever happens to an object, its final motion will be rest, right? Now, that makes sense on Earth, right? Because we have forces like drag and friction that slow objects down. Those are forces. Drag and friction are forces, right? That change an object's motion. But if there are no forces that slowing or changing an object's motion down, its motion will continue on and on in the same way forever. One great example is the Voyager probe, which has actually left the solar system. It's the very first man-made object that has left our solar system. And on it, strapped to it, is a golden record that has sounds of babies and different kinds of music that we've made from all different cultures since basically the beginning of civilization, or at least since we've been able to record stuff. And so that is kind of cool, right? But this object, this Voyager probe, is just going to be continuing in space on and on forever without any power source, simply because its motion has already started and there's nothing in space, no friction, no drag to slow it down. Now, obviously, if it collided with a star or a planet or an alien spaceship, its motion would change, and then it would read the little disc, hopefully, and discover what's going on with it and play it and realize that we're pretty cool. You shouldn't conquer us, okay? So now, I'm going to go to this definition that says an object's motion cannot change unless an unbalanced force is acting on it. If you go to the next slide, balanced forces simply mean that the net force on the object, the total force, if you add up all the forces vectorially, because remember, force is a vector. So if you add up all the forces on an object vectorially, the sum is zero, right? So in other words, if you have a fellow standing here, right, and he's got what's called a normal force pushing up on him. The ground's pushing up, right? And then he's got his weight, right, pushing down on him, right? Then you would say this force is balanced, right? However, if instead we're doing a tug of war, right? And let's say that I have, Bobby is pulling from this direction, right? And then I have Sally pulling from this direction. And Sally's pulling with, let's say, 10 Newton force, and Bobby only a 5 Newton force. That's unbalanced, right? That means that the net force, or force net, is going to be equal to 5 Newtons in this direction, and me, whoever this is standing here, is going to be accelerating in one direction, okay? So balanced forces, the forces always cancel out. There's no net force, meaning there's no acceleration, meaning the motion doesn't change, okay? That's what a balanced force means. Now, if you go to the next slide that says implications of Newton's first law, we've talked about this a little bit, but I just want to reiterate because I think it's really neat and special. So what happens to a ball that you throw in a place with no gravity or air resistance like outer space? The bottom line is that ball will just keep going and 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 going in a straight line forever, and nothing is going to deter that path, right? Because why? Once again, there's only one thing that can change an object's motion, and that thing is a force, okay? And we hinted at this one too. Why does it seem like Newton's first law is violated on Earth? Because, dude, we have friction, right? We have friction, so everything's going to come to a rest at some point. We have drag. Everything's going to, the air is going to slow things down until it comes to a rest, even if the ground doesn't, right? So most people are like, no, this is wrong. This is wrong. This like violates everything that I see in the world, right? Well, most people forget that you're seeing forces that you don't usually think are forces. Very few people look at a ball rolling on the ground and just are thinking of frictional forces. So when from this point on, when you see a ball rolling, right, I want you to remember that this ball does not actually, so let's say the ball is rolling in this direction, right? The ball does not have a force in this direction. No, he only has a frictional force slowing him down. And that's why eventually the ball comes to rest. Okay? Hope that makes sense. So, if you guys could advance to the next slide that says Newton's second law, okay? What's Newton's second law doing, okay? Newton's second law is saying, okay, I have this concept that only forces can change the motion of an object. Only forces can cause an acceleration. But Newton's like, that's not good enough because I can't calculate anything with that, right? So he's like, I want to take my first law and I want to put it into an equation form, right? And so he says that the sum of forces, right, this little sigma means sum, the sum of all forces equals mass times acceleration, right? Another way to say that is F net is equal to mass times acceleration, okay? And this is brilliant what he's done here because he's saying now, all right, if I'm going to get an acceleration, I need a force, right? The bigger my acceleration, the bigger the net force that I need, okay? But obviously, the force is not the only thing that comes into a play, right? Because if I'm over here trying to move a marker, right? It's very easy. The marker's at rest, marker's in motion. Very, very easy for me to change the motion of this marker, right? But what would it take for, you to change the motion of me? Like, what would have to come through this room right now and slam me away so that my motion actually changes, right? It would take something more significant, and definitely more significant than a little push like this, right? So Newton realized I need this other term called mass, right? And mass has a property called inertia, right? Inertia is basically how lazy is an object. The more massive an object, the more inertia it is, meaning the less you want, the less its motion wants to change, right? A big guy like me, super, super lazy, right? My motion doesn't want to change. A small guy like this marker, little inertia, its motion can change very, very easily. Okay, so that brings us to airbags, okay? We talked about this before, and the question is, how does Newton's second law determine whether or not airbags are helpful to you in a car and how it can actually make you safe, right? So what actually is going on over here, right? So what does an airbag do? Well, here, the reason is, what's happening is your head's going at a certain velocity, right? And so when you, your head slams into your dash, right? Or your windshield for that matter, it's going from, 65 miles per hour to 0 miles per hour almost instantly, right? That is what creates that acceleration right there. So going from high velocity to 0 velocity in a small amount of time, that's a really big acceleration, okay? And a really big acceleration means there's going to be a really big force applied to your head. So what do airbags do? Airbags simply reduce the acceleration by increasing the time in which your velocity reduces, thereby decreasing the force that's on your head, okay? All right, so if you guys could advance to the next slide on equilibrium. I just want to talk a little bit about basically, this is just another way to phrase when objects have balanced forces, right? When an object has balanced forces, in other words, like this situation over here, without Bobby and Sally, but with one normal force and one weight going down, and they're equal, and those forces are balanced, you say the object is in equilibrium. This is a term that will come up a lot. So just to be totally clear, equilibrium means the object has balanced forces, okay? Means there will be no acceleration, there will be no wobbling, right? There will be no falling, okay? So if an object is in equilibrium, there is no net force, which means there's no acceleration. People who are civil engineers and structural engineers and even mechanical engineers, they like equilibrium, right? That's the whole goal of living in a society where people are safe, is that the forces on all the objects are balanced in such a way that you're always in equilibrium, okay? So if we can go to the misconception question number 1 here. Can an object be moving and still be in equilibrium? Okay? All right. What do you think? If you give you guys a second to think about it. Okay. Here's the thing. What about this guy? This was my guy that I threw in outer space, right? He's moving. He's got some velocity. Who knows what it is, right? But he's flying away in outer space. But is there any net force on him? No. There's no net force, right? He's just moving. Gravity's not acting on him. Friction's not acting on him. How do you know? Well, his motion isn't changing, right? The only way his motion could change is if there was a force. So this guy has no net force, so he is in equilibrium, but he's still moving. So you can have an object that is moving but in equilibrium. Another example is a plane, right? So let's say that I have a plane, right? You have some force from the engine propelling it forward, and you have some drag force pulling it backwards, but it stays at like 500 miles an hour, right? This object has balanced forces, the same force going forward as the same force going backwards, right? And yet it's still moving. So this is a common question that shows up on MCATs and basically any kind of physics exam that's trying to be tricky with you, because people have a misconception that if an object's in motion, it can't be in equilibrium, but it can be, okay? And that is my intro to Newton's first 2 laws, okay? I'm gonna leave it there, and in the next video, we're gonna talk about what actually are the real forces in the universe, okay? What are the things fundamentally that are causing an object's motion to change? And I look forward to talking about that in a bit.